This is a demonstration of crossover depth. And the relevance of crossover depth to earth sciences is that magma has a crossover depth at which it will sink into the mantle and not be able to rise. Now for our demonstration, obviously we can't use magma, so we are going to use this little contraption, a balloon with some weights. Now the weights are here just to give the balloon enough sinking power that it's going to be able to sink when it gets to the middle of our tube. If I could do this in the ocean and I had a long distance down that I could go, a very long water column, I could just take an ordinary balloon, no weights, and I could just keep pushing it down, 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 down until we got very, very deep, a kilometer deep, or however deep it would have to be. Now I don't have that much space. I need to get my demonstration done here in a tube that's a little over a meter high. So I need to have this crossover depth be visible somewhere near the middle of the tube. So I've adjusted the weight on the balloon so that hopefully it's going to achieve crossover depth right about here somewhere, and then you'll be able to watch it. So up here I want it to float, and by the time it gets to the bottom I want it to sink and not be able to rise. Now the air inside the balloon is going to represent magma. Now this is kind of hard to understand because air and magma are very, very different. The thing that's the same about the air and the magma is that they're compressible. When you squeeze them, they can get smaller. Some things are not very compressible. If I were to squeeze this board or a rock, for example, they don't compress very well. Some things are very compressible. If you've noticed, if you eat a slice of fresh bread, it's very, very puffy, and your mouth is full at first, and then as you chew, basically you're like, where did the bread go, right? Some things can take up less space. And so air and magma are compressible, and so the thing that's going to squeeze our air is the pressure of the water. So when the balloon gets to here, it's going to have all this water pressing down on it, and at the top it's not going to have any pressing down on it. So as it goes further down, there's going to be more and more water pressing on it, and the pressure on top of and around the balloon is going to increase to the point that the balloon would actually shrink a little bit. If you could measure very carefully as this went down, you would see the balloon shrinking a little bit. Okay, so the water column is going to represent the pressure of the mantle. So water, a tube of water is going to represent the rock of the mantle, and the air inside here is going to represent the magma. Now this could be a little confusing because water and rock are very different, air and magma are very different. But the idea of crossover depth of this is the same, whether using air or magma or whatever. It's the same kind of principle. Things that are more dense are going to sink. So let's fill our tube here. Okay. So here's our model of the mantle. So here's our little bit of magma in the mantle, and at the top it's floating. Magma will rise at the top of the mantle. Now I'm going to push it down a little bit, see if it'll still rise. Yep, see it going back up again? Right to a certain depth, magma will rise. It's not compressed enough yet. It's compressed a little, even this much. It's going to compress a little, but not enough to make it not able to rise. So I'm going to push a little more. Somewhere here we will reach a depth where it will kind of stay where it is. Well, it looks like we may have already achieved crossover depth. There it goes. So it's just going to keep going till it hits bottom, or in the case of the Earth, it hits the outer core. Now I'm just going to put my hook through that binder clip. There we go. Bring my little magma back up, and we'll try it again. Okay, let's try this again. Push it down a little bit. Still rises. We're going to try to find neutral buoyancy first. Oh. Almost. It's very, very hard. There's only one point, one very specific point at which it will stay right where it is. It's kind of a challenge to see if you can find it. That's close. Now it's going to come up a little further. There you go, that's pretty close. Alright, so let's give it a push. Doesn't take much once it reaches a neutral buoyancy. There we go. It's begun its downward journey. It's hitting the sides a little bit. It's stopping every little bit because it's rocking back and forth and it's hitting the side. And there it goes. So the crossover depth was right about here. That neutral buoyancy point is the crossover depth. Right about there.